Alright, we're going to go ahead and get started.
This computer works with someone
It does?
It does, yeah. Oh, wait.
Well, you're not logged in.
Yeah, it's logged in.
I mean, it's logged in, it's not.
Okay.
That's what they're all doing now.
Okay, we're gonna, so hopefully, we got about an hour before we actually need to start doing stuff with inventors, so we'll hopefully we can get somebody found and we'll fix this issue. If not, we'll have to kind of adjust what we're gonna do, but it won't be the end of the world if we can't actually do any CAD today. So, alright, we're gonna start with the mechanisms handout. It's got the red robot on the front. Basically, we've got three segments that we've been doing this whole class, right? We've got the engineering stuff, we've got the COTS stuff, and then we've got the actual inventor portion. So we've kind of gone through all the engineering topics that I wanted to go through in the class. So what we're going to be covering in the engineering segment is different styles of mechanisms that are specific to FRC robots. Now we're going to be focusing on FRC, however a lot of this stuff applies to FTC too. It just has to be scaled down in some way. So we're going to start talking about mechanisms here. Once I get this out of my face, go away, go away. All right, so what we're going to talk about today is we're going to talk about intakes. Okay. Now most FRC robots and FTC robots have to take a game piece, typically from the floor, and they have to pull it into the robot or pick it up, or they need to gain possession of the game piece, basically. So, and this is pretty universal across all FRC games. There are a few games where you know, you can receive game pieces from a chute or something like that, but it's quite a bit more common and quite a bit more effective in competition to pick game pieces up off the floor. So there's basically two styles of intakes or pickup mechanisms. I said there's active and there's passive. So passive would be like a scoop, so where you just run into the game piece and it picks it up. I would also, for the purpose of what we're talking about here, I would lump just grippers into the passive category. You have to drive up and then close the gripper on the game piece. I would still call that a passive intake. It's not technically, but for our purposes here, that's what I'm going to lump those in that category. Basically, if you go into FRC with a very small number of exceptions, a passive intake's a bad idea. Tons of teams in FRC and FTC try it every year, and it never works. Teams that win have active intakes, teams that lose have passive intakes. It's pretty cut and dry. So we're on Stellar, unless we run into some sort of special circumstance where a passive intake would actually be an acceptable solution. 2015 is the most notable example, and there's a lot of reasons why passive intakes worked in 2015, but also at the end of the day, you still ended up seeing most successful robots with active intake anyways, even though passive intakes were still quite a bit more effective than they usually are. So we're only going to, for the purpose of this segment, we're only going to talk about active intakes. Now, what I mean by an active intake is basically something that has a continuously spinning wheel or roller or set of belts or something that basically you turn it on, it starts spinning, and you basically just drive your robot into the game piece and it pulls the game piece into place. Right? That's what I'm calling an active intake. We had an active intake last year on Arcturus. We had an active intake for our gear mechanism the year before. Alpha Centauri, which a lot of you guys don't remember, but Alpha Centauri had an active intake, which we're actually going to talk about a little bit. And by the end of the season in 2015, we added an active intake. So there's a lot of, I should go over terminology a little bit here. There's not a lot of well-defined terms when it comes to intakes because this is not a engineering idea, right? I mean, no company out there has to pick up balls off the floor with a roller, right? That's just not an application that you really ever have to do outside of a robotics competition. Although I was looking, there is a robot that's for practicing tennis for like professional tennis players, and it basically runs around. It's like a little Roomba, except it has a roller and it picks up tennis balls. I can't remember if that company was started by FRC alums or not. I don't remember how I heard about it. But anyways, so outside of that one product, you never have to pick up a ball off the floor with a roller. But there's basically two ways, and you'll see both pretty much regardless of the game. Basically, there's what I'm calling a horizontal intake, which is what's pictured on the front. I'm actually just going to pull the picture up here. This might be a better picture. No, I don't want to go with it. It's not even on the page. Okay. Guess we're gonna have to do this. Alright, so this is Team 1114's robot from 2015. This is what I'm gonna call a horizontal intake. And by horizontal intake, I basically mean that the axis of rotation of the rollers, right? You can see the rollers are these orange wheels right here, 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 and here, and on this picture. Basically, the axis of rotation is roughly vertical. Roughly, not to be exact, but roughly speaking, they're vertical, so the wheels are kind of laying on their side, right? That's what I'm calling a horizontal intake. Now, that's what's on our robot this year. Arcturus has horizontal intake. The vast majority of robots this year had horizontal intakes. Okay. Now, the other style, if you flip your sheet over, and I'm just going to use this. Oops. All right, this right here is one of my favorite robots. Like this is actually one of my top 5 favorite FRC robots from 2012 T971. This is what I would call a vertical intake, and there's really no rhyme or reason to why I call it that. And like I said, there's not a lot of agreement on what these things are called. But I would call this a vertical intake because it's more of an upright kind of an orientation, right? The rollers are rolling in kind of a what you would call a normal direction, what I would call upright. So basically, a horizontal intake. Well, actually, I'll get that in a minute. So a vertical intake like this, anyways, so a vertical intake like this essentially works best for balls, right? Because it can roll the ball in to the robot, and they're nice because they can be the full width of the robot, right? So you can kind of just pick up a game piece anywhere along the front of your robot. This particular design, the ball would roll under this front roller, it would get pinched between the bumper and this front roller, and then it would move up and into the robot. That's a fairly common design. That's what we did in 2016, which is the other picture on your handout. Basically, there's other designs though where you could have a plate, like a ramp underneath those rollers that the ball would actually roll up rather than interfacing with the bumper. You could have a ramp that the ball would roll up. You could also use another set of rollers rolling the opposite direction so the ball gets pinched between 2 rollers. That's also a fairly common design. A lot of this depends on the game piece. You're never going to see 2 intakes on 2 different robots that are exactly the same in any given year, even given the same game piece. They're all going to be slightly different. However, a lot of the designs follow pretty consistent, I guess, conventions, because they've worked year after year after year. So in this case, I'm using roller generically to describe any kind of rotating thing that interfaces with a game piece, right? So FTC's Hercules' robot from 2 years ago had more of a paddle, right? Had more like paddles on it. Still, really, I would still call it a roller, right? I mean, it's accomplishing the same thing. Something that's common, is a fairly easy and low-tech way to do a roller is to take a shaft and to put a whole bunch of like small rubber wheels on it, right? You'll see a lot of those, but that's easy. You can do rollers more like this, which is a straight bar with end caps. That's a proper drum roller. You could also use belts. Now belts are what I have pictured on your handout. This is from our 2016 robot, Alpha Centauri. Basically, we had drum rollers just like this, except we had rubber on them that created a little groove. And then basically we had round, they're clear round polyurethane or urethane belt, which has a lot of grip, that was wrapped in cords, right, so loops. And basically that allowed us to convey a ball from the floor up into the robot. Now, this particular example doesn't need belts because the ball and the rollers were close enough together and the ball was squishy enough that they didn't need to bridge the gap between the rollers. The ball was always in contact with the rollers as it made its way up into the robot. In 2016, it was a little bit different because our bumpers were so much higher. We had trouble getting the ball. The ball had to go more vertically, and the way it worked out with the geometry was that we couldn't get the rollers close enough together that we could accomplish that. So this particular example, I don't remember where the motor is. I think it's behind this part, but basically there's a chain inside of these side tubes that join all the rollers together so they're all run off of one motor. And that's, once again, that's a fairly common design. I would say it's more common for teams to use belts than it is for them to do something like this. But this can save weight because the rubber is fairly heavy, so, and you typically need a lot of it. So not using any belts can save you some weight. Okay, so let's talk vertical versus horizontal, because I said you'll see both every season. So a lot of teams default to horizontal intakes, right? Which is where, even when they're using a ball or something, right? Which is where you've got wheels on either side. Now, the problem with a horizontal intake, and this is a problem this year, and this is a problem every year that you use a horizontal intake, is that when you're driving it, right, you've got to hit the game piece with both sets of wheels at the same time in order to intake the game piece. Because typically the rollers are spinning pretty fast, right? Because you don't want it to take 10 seconds to pull a game piece into your robot. You want to make contact and you want it to be in your robot as soon as possible. So typically you have a pretty high surface velocity on your rollers. And if you're coming up to a game piece, say, and you touch with one roller before the other, the roller tends to send the game piece flying. Right, tends to kick it and it goes rolling if it's a ball, or if it's a cube. In the case of this year, it turns and it gets at a weird angle. So you've got to hit it when you're driving a horizontal intake. You've got to hit it like straight on, perfectly centered. That's a problem because you can't do that. It's just very, very difficult to do that. Now, in the case of years where we're not using a ball or something round, we used Frisbees in 2013, and I actually never saw anybody use a horizontal intake on the Frisbees, just because they're so flat, you really can't get a roller on the side, you have to go to the top. That was a little bit of a weird year, but still, vertical intakes, which with rollers kind of flat, those really aren't good for those, but it was the best I could come up with. Anyways, so in 2016, a lot of teams used horizontal intakes, right? I don't know why. I really don't understand why they did that. They didn't work. Those are the teams that spent a lot of time running around the field chasing balls that they had bumped with one of their rollers and they would fly. Because they were trying to line up on a ball that was this big with two rollers that were designed to squeeze that ball. So the rollers really, they didn't have a big wide opening to hit. But then there were the teams that had a vertical intake who could just run into the ball and it would pull it in and center it. So typically speaking, if you can use a vertical intake with rollers rolling in a more horizontal fashion, do it. If you have a weird shaped game piece like a cube or a tote, you're probably going to have to go with a horizontal design. But you get a little bit of forgiveness when it comes to those types of game pieces because like a cube can't roll away from you. Right? A cube can get bumped and it'll turn, but it's not going to roll across the field where you have to chase it, which is the issue with the ball. And then in 2015, which is what this robot, which is the game this robot played. The totes were heavy enough that they really didn't move if you bumped them, so the horizontal intake was really a pretty good design that year. There were a couple of teams this past year with First Power Up who used horizontal or vertical intakes, where there was a roller on the top and a roller on the bottom, and they pulled a cube in, I guess, from the top and bottom. They were difficult to get working, but they did work, so a lot of teams didn't do those. And the most, 1678, the most prominent team that I know that used that design ended up switching to a horizontal intake just because I assume it wasn't as effective. I really don't know the details there, but that's what they did. So, this is a difficult thing to kind of summarize just because of how much variety there is when it comes to intake mechanisms. However, there's some obvious lessons to learn in terms of, if it's a ball, use a vertical intake if you can. There's a couple other takeaways that I want you guys to get. One of them is the difference between wheels and drum rollers that are driven like the 971 robot, right? Drum rollers that are driven individually, or drum rollers that are connected by belts like our 2016 robot. Those are all options when it comes to designing an intake in the season. We're going to be looking at all those different options. Another thing to remember is that typically speaking, an intake, a good intake, will be some sort of a folding mechanism, right? So you'll notice this intake is outside of the bumper, right? This mechanism has to fold up and down. So last 2 weeks we were working on a project that we called the pneumatic joint. Now that pneumatic joint, that project is a mechanism that you would basically use to actuate a mechanism like this up and down. Now this specific robot actually had it geared. They had a motor driving it up and down. I don't know why, but that's what they did. Yeah, I really don't know why they did that, but that's what they did. Actually, no, I do know why they did that. That had to do with the end game, but don't worry about it. Okay, anyways. Did I have anything else to say about that? Any questions? Alright, so next we're going to talk about planetary gearboxes. Now, this is, out of all of the CAD segments in the class, this is the most important one. So if you've been sleeping for all of the other CAD segments, Wake up and listen to this one, then you can go back to your nap. All right, I'm going to Vex's website. I'm going to pull this up and then we'll get back to it. Okay, gearboxes. All right, so who knows what a gearbox is?
We made a 4-stage
I
one.
made one.
We made one, yes we did. So all of you should know what a gearbox is. So that's what we call a spur gearbox, okay? And the reason that we call it a spur gearbox is because you use spur gears. Go figure. We're going to talk about a little different style of gearbox called a planetary gearbox. Now, a planetary gearbox still uses spur gears, but it's in a very special arrangement. So, if I'm going to draw gears as circles, but do you guys remember when we talked about internal gears, like fairly early in the class? You guys remember that? We call it a ring gear. Okay? So, if we have a ring gear, this is our ring gear, okay? It's got teeth on the inside. Now, this is still technically a spur gear. It's just called an internal spur gear. Okay, so it's still spur gear. If you can run a normal spur gear on the inside, right? The two mesh, an internal spur gear and an external spur gear mesh, and that's kind of the point because there's no actual way to mesh to internal spur gears. And there's just no way to do it. So, if you can come up with some geometry to make that work, be sure to let me know. Okay, so this is what we call you don't normally call this a ring gear. You just call it an internal gear. In normal, just everyday talking about an internal gear, you call it an internal gear. When you're using it in a planetary gearbox, this is what's called the ring gear. Okay, for obvious reasons because it's a ring. Okay, so next we have a gear in the middle. This is spur gear. This is called the sun gear. And why that is will become apparent very shortly. Around the sun gear, we have, go figure, planets.
No way.
Wait, are you kidding?
It's no joke, folks.
It all makes sense now.
Now, depending on the size of the ring gear, like the number of teeth, and the size of the sun gear, which we'll get to in a minute, there might be different numbers of planet gears. There might be 2, there might be 3, there might be 4, there could be more than that. Typically you'll see 3 or 4. Okay, so now this is the arrangement of gears. So typically, now this is not always, but in FRC use, you connect your motor to the sun gear. Okay, so your motor's going 18,000 RPM or whatever it's going super fast, right? And you want to slow it down, you want to slow it down, decrease speed, increase torque, so you can use it for something useful. Okay? So, as you can imagine, if you run this internal gear, these outside gears are going to kind of roll around the outside as this inner gear turns. And then this ring gear is held stationary, right? So the ring gear is typically part of the like the structure of the gearbox. So if you look at this gear, this is a planetary gearbox on the screen. This like little section here, the ring gear is machined inside of this box, okay? So what we have another part that goes on top of this that we call the carrier plate, okay? And the carrier plate essentially has pins that just support the centers of the planet gears. Okay, the planet gears can free spin around the pins, okay? And the carrier plate is just a plate of metal. So then as this middle gear turns, these roll slowly around and they cause the carrier plate to turn. Okay, and then basically what you do is you attach the output shaft of your gearbox to the carrier plate. Okay, so the carrier plate rotates slowly, and the sun gear rotates quickly, which that's what gives you your gear reduction. Now, what you can do, yes.
Is the calculation for torque and speed the same, even though there's three? Does it change at all? Or do you just assume that there's only one of them? How does that even work?
I have to remember, so here, I guess I should go into this. It's not quite so simple because you're not always fixing the ring gear and using your carrier plate to drive something. Sometimes you fix the carrier plate and the ring gear is what you want to drive. And there are applications where that's how you do it. If you're doing that, then yeah, it's just basically the gear ratio between this gear and the ring gear, right? I mean, it just the planets are really just idlers. They're not even really planets; they're just idlers at that point. But the gear ratio for the carrier plate's a little more complicated. It's close, but it's not quite. It's like 1 minus. I didn't put it in the handout, and you have to look it up. And then there's a reason I didn't, because planetary gearboxes are really complicated. We don't typically design them because we don't have the ability to manufacture them. So, but you can look it up. I mean, there's websites that tell you what it is. I don't remember what the equation is off the top of my head because I haven't done much with them.
Okay.
But yeah, to answer your question, no, it's not simple. It's a little bit more complicated equation, but it's pretty straightforward. Okay, so now that's one stage. Now basically, the smaller you make the sun gear, with a given number of teeth in the ring gear, the smaller you make the sun gear, the higher reduction you're going to have. Okay? When you're looking at a planetary gearbox, the gear ratio is not dependent at all on the planets. But the number of teeth, how big the planet gears are, that's just corresponding to fill the gap between the sun gear and the ring gear. So when you're looking at the gear ratio between the gear ratio of your gearbox, the size of the sun gear and the size of the ring gear are the only things that actually matter. Okay. Now, in our spur gearbox project, we designed a 2-stage gearbox, right? So we had the motor, then it went through 1 stage of reduction, then it kind of handed it off to a smaller gear and did a 2nd stage reduction. You could do the same thing. You can do the same thing with planetary gearboxes. So what you can do is basically you attach another sun gear to your carrier plate. So you've got your sun, your ring gear, your planets here. You've got a carrier plate holding the planets. Then you put a sun gear attached to the ring gear, and you run that into another stage, right? And you do however many of those you want, and then output shaft. Okay. Does that make sense? Everybody clear on how planetary gearboxes work? All right. So let me ignore. Okay. Okay. So what are the advantages of the planetary gearbox? Well, first of all, they're compact, right? They don't use much space. Because you've got kind of all the gears that are they're inside of each other, they stay in a very compact form factor. It's also kind of nice because the output shaft and the input shaft are coaxial. Right, so the center line of the input shaft of the motor is along the same line as the output shaft, right? In our spur gearbox, the motor was up here and our output shaft was down here. Okay, that's kind of nice. Once again, mostly for space-saving reasons, but occasionally you need to be able to have something that's coaxial for some reason. But once again, that's really just space savings. Now, because the gearbox is smaller, they also tend to be lighter, and they have an advantage over a spur gearbox. So let's look at what a spur gear arrangement to get a similar reduction would look like. So we have a sun gear, or a pinion in this case, which is the same size as the sun. And then we have a large gear, right, with teeth on it, really bad teeth. It's not a very good gear.
It looks like
So
a
that
big
one's
sun.
the size of the sun?
Yes,
Okay.
a gear that's the size of the sun.
This is pretty massive gear reduction.
Right. You also have to factor in gravity and stuff when you're working on your design, because the gear is going to want to pull the rest of your structure into it and start nuclear fusion.
Oh, God.
You gotta worry about nuclear fusion right here where you're going to interface with your output.
Is there a tool for that in Inventor?
Yeah, you just do an FDA and it'll tell you where nuclear fusion is going to occur.
You know, that solid works.
Okay, so let's assume, and I like Caleb's question earlier, I don't know the equation off the top of my head. I probably should have put it in the handout, but I was running out of time this week, so the handouts are pretty short. But anyways, let's assume the gear ratio here is the same as the gear ratio between the sun gear and the carrier plate. So, how many teeth are in contact with each other in this arrangement?
Like about 2.5.
It's just one pair. It's just one pair. There might be a situation where you have two contact points. As it transitions from one tooth to the other, I don't quite remember, but for all intents and purposes, I've got one tooth of the sun gear in contact with one tooth of the spur gear at any one given time, and that's it. Okay. How many contact points do I have here? Well, with the sun gear. We're looking at the sun gear here.
Ranging from 3 to 6. Or
Right.
27.
So basically, so basically you've got one set of mesh teeth here, and then here you have, 3 mesh teeth. I mentioned some planetary gearbox only have 2 planets. Some have 4. You could have 5. The ones that we use don't, but some could. Actually, no, I don't think any of ours do have 5. But anyways, so basically you got more teeth in mesh. So what does that mean? That means for the same size gear, you can handle a lot more load. Because where all the load has to be taken up by one set of teeth here, the load can be taken up by 3 sets of teeth, even though you have the same gear reduction. Now, does that mean, well, basically what that means is for a planetary, to get the same gear ratio with a planetary gearbox as you would with a spur gearbox, you can use smaller gears. Right? I mean, in this example, you could, in theory, use gears that are 1/3 the size of the spur gear arrangement. Right? Which is pretty significant. Now that there might be some, you might not be able to go quite that far, but generically speaking, you can use smaller gears on a planetary gearbox than you can in a spur gearbox. And basically what that means is the planetary gearbox was already smaller and more compact than the spur gearbox. However, now it's even smaller and more compact and it weighs less because you're using smaller gears. So planetary gearboxes have a lot of advantages. Now, what are the drawbacks? Because if there were no drawbacks, we'd never use a spur gearbox, right, ever. Nothing?
Well, I found him, but he's working on it, and it's not looking like it's gonna be fixed anytime soon.
Okay, well, we'll work on it. Okay, well, thank you for doing that, by the way.
Yep.
Would you make sure the GoPro is pointed? I can't tell. It's recording, so don't drop it on the floor. But okay. Right. Okay. Drawbacks. All right. Number 1, they're very complicated. Okay. The spur gearbox that we designed a couple weeks ago. I mean, that was not hard. There's not a lot of parts there. It's pretty easy. Other than the gears themselves, we can make all of the parts on that thing. We can make our own gearbox, right? So if we need something special with a special gear ratio that we can't buy, you know, we can just make our own, right? That's nice. So Planetary Gearboxes are very complicated though, and we cannot make them. So you have to buy them off the shelf, and when you're buying something that's that complicated, they tend to be very expensive. Because you've got gears rolling inside of gears and all that stuff, they have to be made very, very precisely, which makes them even more expensive. And in addition, I talked about Planetary Gearboxes being smaller and lighter than spur gearboxes. In some cases, that's not actually true, because the ring gear has to have structure on it. You know, there has to be some sort of an outer structure, and that can add a lot of the weight to the design. So occasionally, Planetary Gearboxes, especially for small reductions, like really low reductions, like reductions that you could accomplish with one stage spur gearboxes, they're competitive in terms of weight, and so Planetary Gearboxes are not always advantageous in those applications. But the main drawbacks are cost and complexity, and the fact that you have to buy them off the shelf and you're kind of at the mercy of what's available. So I wanted to go into quite a bit of detail there because we're going to use Planetary Gearboxes on nearly every mechanism that's not our drivetrain. Right? I mean, drawbacks being what they are, we're still going to use them. We have used them on every robot. So we're going to talk about what the off-the-shelf options are, and whether you guys end up actually working on CAD for next season, or if you're doing something else. Basically, everybody's going to help put the robot together. So everybody's probably going to end up handling a Planetary Gearbox at some point. So it's important to understand the underlying concepts, because we've never really sat down and taught everybody how to put the Planetary Gearboxes together. And so, yeah, and they're not simple. So, yeah, you've done it. I know Liv's done it.
Don't hold it upside down.
Yeah, the whole thing will fall apart. Okay, so we're going to talk about a few of the most common options. Now, FTC, there are Planetary Gearboxes that are available for you guys too. There's a few different options. Yes?
Could you use a FRC Planetary Gearbox on an FTC robot?
Yeah, I think so. More recently, a lot of FRC stuff is getting used on FTC robots just because better. I mean, the market for FRC was already there, so it's pretty easy to just adapt it for a smaller robot. So, but there are some FTC specific Planetary Gearboxes that are quite a bit smaller, because no motor in FTC comes close to the kind of power that an FRC motor would have. So there's no reason to add, you know, FRC stuff's just too heavy and too big. So, all right. This product right here, it's called the Versa Planetary. For obvious reasons, it's a Planetary Gearbox and it's versatile. Most of I don't know if you guys have picked up on it yet, but most of all of X-Pro's products start with Versa. It's just Versa this, Versa that, and I don't know, a couple last year maybe they just gave up and they just said Versa everything on their front page. That was their like tagline. Yeah, everything's Versa. But anyways, the Versa Planetary is without question the most influential off-the-shelf part that's ever been invented in FRC. Like, if this product changed the way FRC worked, period. Like, this product was launched in 2013. Nearly instantly, everybody started using it. They've made improvements to it since then. Now, it is very rare to see a robot that doesn't have one of these or multiple of these on them. For a Planetary Gearbox, they're fairly cheap. They're affordable. I mean, they're still expensive, don't get me wrong, but they're affordable to the point where most teams can use them, and they're affordable to the point where they outcompete in terms of price even off-the-shelf spur gearboxes in most cases. So the Versa part of this will become apparent fairly quickly. If I can find their diagram. That's a terrible diagram. All right, never mind, I'm just gonna use the picture. Okay, so this is the first Planetary Gearbox. This is actually version 2. We have both version 1 and version 2 stuff upstairs in our collection. The way you can tell the version 2 versus the version 1 versus the planetaries is these bumps. See how there's this kind of like little dip down, this low spot? The version 1s are completely square all the way around. They don't have these little like humps. The reason they put those humps in there was just to shave a little weight off the outside, because the flat surface really didn't do anything, so they just kind of shaved the whole thing down, made it a little smaller. But they left the bosses here for these tap holes. But anyways, so basically the Versaplanetary is a kit, and you can buy different components for it, and you can kind of just build the whole thing up. So this back section here is just an adapter block that you attach your motor to. There's a set of collars, which are like they're just little clamping things, and they act as an adapter between the motor shaft and the input shaft that attaches to the sun gear in the first stage. So basically there's an adapter, and it can adapt between any of the motors in FRC to their gearbox. So you can use any motor. Well, any non-geared motor. There are a few, we talked about motors last week. It can interface, the Versaplanetary can interface with any of those motors. You buy the gearbox, you get a bag of little parts that have all the little adapter pieces to adapt to any motor. Okay, so Versaplanetary Gearbox, you put any motor on there. Now, that's good because it means you don't have to buy different gearboxes for different motors, which when we go and look at some of the other options other than Versaplanetary, which I'm not going to go into a lot of detail on because we're not going to use them, but you have to buy a specific gearbox for a specific motor, okay, which is kind of a pain. The Versaplanetary can be used on any motor. And what that means is that when you're in the season, if you've got a mechanism that's not powerful enough, you can change the motor and put a more powerful motor on it if you want to. Or if you want to go to a smaller motor to save weight or save battery voltage, you could do that too. Or if you're using 550s, you know, for something and you're smoking them out because they're kind of crappy, you could switch to a bag motor, right? Midway through the season, you can just unbolt the 550, solder your wires on your motors, and bolt the motor up in the pit at a competition if you want to. Okay, so you can attach any motor to a Versaplanetary. Next, we've got the output shaft, which is this block on the end. The output shaft, which is this square piece and the actual shaft itself, you can buy different shafts. You can buy 1/2-inch hex, which is fantastic because we use a lot of 1/2-inch hex stuff. You can also buy 3/8 hex, which is for smaller mechanisms that don't need as much torque. It just saves weight, so you can use 3/8 hex. That's also pretty common. You can do a round shaft if you like using round shaft with keys. Those used to be more common. Teams used to do a lot of machined keyways and stuff, but since then, in the last 5-6 years, hex shafts have become pretty common to the point where they've taken over. And there's a couple different styles of there's 1/2-inch round keyway, and there's the sim output, which is actually 8mm round with the keyway. Basically, the gearbox can imitate a sim motor. You guys remember what a sim motor is? The big ones we use on our drivetrain. Basically, the bolt pattern to the front of this thing is the same as a sim motor. So any place you can attach a sim motor, you can attach a Versaplanetary, and that was done intentionally. And so basically, you can use an option for the Versaplanetary that has the same shaft as a sim motor. So if you wanted, a sim motor is a fairly large, low-speed motor. So if you wanted to take a smaller motor, gear it down to the point where it's about the same speed as a sim, and replace a sim with it, you could if you wanted to. Now, there's not a lot of cases where you do that, just because typically a small motor and a gearbox is going to be heavier than a sim. Actually, it might be close. I actually don't know. I have to check on it. It might be close. Anyways, okay, so you can attach any motor to a Versaplanetary. You can have essentially any output shaft you want. They also came out with some options, some extra stuff where you can take this output shaft and instead of having an output shaft that sticks out, you can kind of have a hollow output shaft that has like a hollow hex hole in it. So you can put a piece of hex shaft in that, looks like a socket, like for a ratchet almost. So you can put a piece of hex shaft that's like really, really long if you're driving, for instance, an intake roller and you want the gearbox to run a long shaft that's got a bunch of wheels on it or something, you can do that without having to interchange between a motor shaft and that. So that adds an extra level of versatility to the output of a Versa Planetary. That's the Versa. Now, really, now that's all great, right? That's like fantastic, right? Any output shaft you want, any motor you want, great. Well, that's not even the best part. The best part is the fact that this middle slice, this is a ring gear. Inside of this is a sun gear and a carrier plate and planet gears, and the ring gear is machined right into the outer piece of aluminum. What you can do, they have, I don't know, 6 or 7 different gear ratios. So you buy the ring gear, there's one ring gear for any gear stage. Andrew, are we good?
Huh? Oh, is everyone there? I don't think some are.
Looks like it's working on my system.
Mine's not working.
Well, some are working out, some are. It looks like that computer. That one.
Mine's
is not.
working.
Oh, we might have it working now.
Oh, I
Thanks.
forgot my USB.
Like you said, restart.
Okay.
Mine's not.
So whose systems are not working? Raise your
Mine's
hand.
working.
Raise your hand if it's not working. Ben's still working.
Ben, you
Somebody
can
else?
trade me. I don't have my flash drive.
I don't have my flash working for me either.
Okay.
He gets kind of stubborn.
Mine isn't working.
All right. Anyways, back to what we're talking about. So there's one ring gear. Every Versa Planetary uses the same ring gear. There's not like multiple different kinds of ring gears, and they did that because it would just be confusing. So there's one ring gear, and then basically you can swap out the carrier plate, planets, and sun gear as like a kind of a little unit. They come in a little bag, and they're all kind of assembled together, and you can replace the actual group of gears here in the middle. Now they all have a common. The sun gear has like a spline on it, which kind of looks like a gear, but it's actually just a way of locking shafts together. It's kind of like having a bunch of little keys around the outside. It has a spline. So the sun gear has a spline on it, and the carrier plate has a spline on it. And basically, you can add, as you can see, this gearbox has this little slice in the middle, and this whole thing bolts together. So you can unbolt it, you can add more ring gears if you want. And then you can take more gear sets and you can just stack them up, right? Now, practically speaking, you're not really ever gonna go above 2 stages. However, teams will go to 3. You get by on 3 and it's not gonna be practical anymore. But you can do 1-stage gearboxes, you can do 2-stage gearboxes. Those are recommended by VEX, that's what it's designed to handle. You can also do 3 stages if you really need to, for some reason. But it's kind of outside the design specifications, but if you know what you're doing, you can get it to work. But basically, you can add and remove stages as you want. Well, then they also sell, they're selling different gears that have different gear ratios. So you can buy a set of gears in the middle here that gives you a 3-to-1 reduction. You could buy 4-to-1, 5-to-1, 7-to-1, 9-to-1, and 10-to-1. Right? So you can go all the way from 3-to-1 reduction in one stage up to 10-to-1 reduction in one stage, which is pretty significant. Then you can add and remove stages if you want. So you can go to, and then each one of those stages can have a different gear ratio. So using combinations of gears, you're just multiplying the gear ratio of all the gear stages together to get your overall gear ratio, right? Because just if I've got a 3-to-1 here and I've got a 3-to-1 here, that means I'm getting 3 times 3, I'm getting 9-to-1 overall, right? So basically, you can swap out gear sets, change the gear ratio, and you can do all of this in the middle of the season, right? So you put a gearbox on your robot. Oh, that mechanism's running too fast and it doesn't have enough torque, right? That's a typical problem is it doesn't have enough torque. Okay, pull it apart, stick a different gear ratio in there, right? You can just do it during the season, and I guarantee you we will. I mean, that's what we always do. Which that has two advantages. First of all, if you need to make a change, you can make a change. And second of all, it means that you don't have to really nail down you don't have to calculate all your torques and do a bunch of engineering and stuff ahead of time to figure out what the best way to run your mechanisms are. Now you still want to, you still probably should, but you don't have to be quite as good at it, basically, because you can always adjust your gear ratio later. You build your robot and you're like, that's just not working very well. You swap out your gear ratios. You try a few different gear ratios if you want to figure out what works best. So in addition, there's a couple of extra products that go along with this. I mentioned the hollow output shaft. It's kind of like an add-on thing. You buy it separately. There's also a back shaft for this, and I don't see it here. I'm not going to go looking for it. But basically, normally you just bolt a motor like this. You see how this motor is just bolted to the back. Normally this is what the gearbox would look like. But there's a special little kit that allows a hex shaft to come out the back side, and then you can drive that hex shaft with basically a belt, right? So you can just have the gearbox, and it's got a input shaft on one side and output shaft on the other, and you can drive the input shaft with a belt. And basically it's designed so that if you want to, I'm going to draw the gearbox from the top, right? So here's the gearbox, this is the motor input stage, here's a couple ring gears, here's the output shaft, right? Normally it's designed so there's a plate, you put your motor over here, and you run a belt from here to here, and there's a shaft here and the motor shaft here. Right, and that's just to save space, because you start stacking up VersaPlanetaries and they get pretty long. I mean, they take up a lot of length. They don't take up very much width, because that's the advantage of a Planetary Gearbox, but they're very long, which is the drawback to the specific design. So doing this, you can kind of wrap it around. We used this product on our intake last year because we wanted to drive a belt reduction to drive our intake rollers. So we actually used this, except we didn't use this plate. We made our own plate and moved the motor kind of like over here. But anyways, that's a product. There's also an adapter, and the adapter replaces this chunk right here. So the normal aluminum motor adapter block gets taken off, and you replace it with this guy right here. And basically what this is it allows two motors to go into a VersaPlanetary. So instead of just one motor, you've got two motors that each have a little gear. They drive a middle gear, and that middle gear drives the sun gear. We used that on our elevator last year. So we had two motors driving our elevator to get more power because our elevator sucked and it needed it. And it still didn't work, right? But that's what we used. We used that thing. So VersaPlanetary, incredibly versatile. Go figure. We're going to use one in our CAD project, which we're going to start here in a couple minutes. We're going to use one. I want you guys to get familiar with the different products associated with the VersaPlanetary, the different things available. I want you to get used to working with the CAD models of VersaPlanetaries. It's going to be the most complicated thing we've imported so far. It's going to be a little bit of a pain, but I'll explain that as we get into this. If there's one thing that you guys pull out of this project, of this segment, I want you guys to get used to working with these, because we are going to use these on a bunch of mechanisms on our robot next year. Like that's just how it's going to happen. So if you're designing something, getting used to using these is going to be the best thing you can do. All right, so with our last couple minutes here, we're going to talk about a couple other options besides the VersaPlanetary, because the VersaPlanetary is not the only option. Now, we're probably not going to use these options, but other teams do for various reasons. So the first one, I'm going to go in a little bit different order than is in your handout. You guys remember BaneBots? They make those little tiny plastic and rubber wheels, like the orange and the green and the blue, that are these. like what's on my screen I'm talking about. Okay, they also make, if you remember BaneBots, that their products are made for like small, like BattleBots kind of things. Not like big BattleBots, but smaller BattleBots. They make gearboxes for those robots. Now, this is a type of gearbox that you have to buy for a specific motor. You guys remember the RS550, right? That was that really, really small, fast motor we talked about last week or 2 weeks ago, whenever that was. That's a BaneBots motor. So you would, for RS500 series motors, because there's an RS550 which we use, there's also an RS540 which I don't know that anyone would use because it's super, super low power. It is FRC legal if I remember correctly, but nobody uses it because it's just a crappier RS550 basically. It's no lighter than an RS550 and it's lower powered, so like why? But basically, for RS500 series motors you can use this. For RS775s, which are FRC legal. Now you guys remember there's a 775 Pro. Now the 775 Pro is not manufactured by BaneBots. However, the it's not RS, the 775 Pro motor is based off of the RS775, which is a BaneBots motor. Okay, so they're the same form factor. I don't know if 775 Pros can interface with these gearboxes or not. I don't actually know that. They might, they probably do, but I don't know that for sure. But anyways, so whatever motor you're using, basically though, you can't use these with a bag motor. Right, if you're using a bag motor, you've got to use a VersaPlanetary, that's your only option, as far as I know. But if you're using a BaneBots motor, these gearboxes, these are not modular, okay? They're called P60s. They also have a P80, which I think, I don't remember the P80. Yeah, the P80 is meant for a sim, and I don't think I've ever seen anybody use a P80. I don't. The P80 is meant for a sim, if I remember correctly. Okay. But basically, the P60. They don't come in as many gear ratios. You can get 3 to 1, 4 to 1, 5 to 1, 11 to 1, 13 to 1. Actually, I think these are new. I don't remember these. Anyways, that's not too bad. There's not as many gear ratios as a VersaPlanetary, but there's quite a few, and there's actually more since I've been to this website, so there's more than there used to be. But basically, they come, you buy one gear ratio, and the gearbox comes assembled. And that's how you get it. You can't change the gear ratio. You have to change the whole gearbox if you want to change the gear ratio. In addition to that, in order to attach a motor to it, you have to press a pinion onto the motor shaft. So the gearbox, the VersaPlanetary has a special clamping adapter where you basically you attach the motor and then you just tighten a screw down and that's all you need to do. Super, super easy. For these, you actually have to press a motor pinion on, which means if you burn out your motor, you typically can't have that, you can't take that pinion back off very easily without a special tool. So typically you've got to buy extra motor pinions if you want to be able to change your motors, which is a huge pain. However, and in addition to that, in addition to its other crimes, the poor P60, this was the gearbox before the VersaPlanetary, right? I mean, this is what everybody used before the VersaPlanetary. This was the best there was. But its other sins include, it doesn't have a 1/2-inch hex output shaft. It's round and it's keyed, which means you've got to either buy stuff which has a pre-manufactured round keyed hole in it that will match, or you've got to machine your own, which is a pain in the butt. In addition to that, it's also not easily face mountable. So the VersaPlanetary has these mounting holes on the front, right? So you get flat plate, you put a hole in the plate for the shaft to stick through, you put 2 bolt holes in, you bolt the VersaPlanetary flat against something. That's 9 times out of 10 how you want to mount it. If you want to mount the side, right, you want to like lay the gearbox on the side of something, then you use these holes here at the top. Okay, so you can face mount it, which is what you're going to do most of the time, but you can also side mount it if you need to. The P60s, you can only side mount. There are ways to face mount, but it gets a little sketchy. you can do it, but you've got to basically take the whole gearbox apart, get different screws, basically replace the structural screws, and then if you want to take the gearbox off, the whole gearbox comes apart because the mounting screws are also the screws that hold the gearbox together. That's the way I've seen it done anyway. Maybe there's other ways to do it, but that's the most compact way to do it anyways. But these are like 2/3 the price of a VersaPlanetary. So if you've got the machining resources, you're using a BaneBot's motor. If it works for your application, it's cheaper. I think they're smaller, they're lighter, they might be stronger than a VersaPlanetary. I don't know that last one for sure. I would say overall they're probably a higher quality gearbox than a VersaPlanetary is, just because they're manufactured for a specific size, whereas the VersaPlanetaries are meant to be bolted together, so the VersaPlanetaries are kind of a little rough around the edges sometimes because they're all bolted together and they're, you know, configurable. But anyways, that's the P60. Then in addition to that, this is a new one. This gearbox came out last year. We actually have one of them upstairs. It's called a 57 Sport. This, according to their website, this was like a partnership between Andy Mark and BaneBots. So Andy Mark had it made, but BaneBots is doing the manufacturing. So it's got a lot of the same advantages that a P60 has in terms of it being more compact. This gearbox is quite a bit stronger than a VersaPlanetary. And actually they have a guarantee that if a gearbox breaks at a competition, they'll replace it. Which is a pretty big deal because you can destroy gearboxes pretty easily at competition. So I've never used them. We do have one upstairs, so it's possible that if we get some application where this works, we might use it. Unlikely, however, possible. These are also slightly cheaper than a VersaPlanetary. They also have a 1/2-inch hex output shaft, which is nice. But I don't, like I said, I have never designed anything with one of these. I'm not sure how the face mounting works. I'm not sure if you can use these screws for face mounting or if you have to do kind of the same thing you did with the P60. But yeah. All right, so that's everything for Planetary Gearboxes. Does anybody have any questions? No? All right, does everybody have Inventor up? Did I bring my flashlight? That was the question. All right, so this is another 2-week project. So we're gonna kind of do this in the same way we have before. We're gonna start with our layout sketch and our some importing, and then next week we'll keep working on it. I will put out videos like we have before of how to go through this start to finish. So let's talk about what we're going to design, and then we'll get into it. So we're going to look at this from the top.
Wow.
It looks so cool.
This is why you need ShamWow. Cleans messes faster than you can say ShamWow.
Oh, I think you can say ShamWow pretty fast. All right. So what we're going to do is we're going to design kind of like a chunk of an intake. Right? We're not going to design the whole intake mechanism because that would take way too long. We're going to design kind of part of the structure, and then we're going to design the roller, and we're going to design the gearbox driving method. We're going to use a VersaPlanetary. We're going to use a CRP drum roller, because I'm teaching the class, it's my product, and you use what I say. But those are the ones we use during the season because they're free, because I donate. So, most of our robots have one or two of those on there, but and they're easy. Easier than Vex's products. CRP for the win. All right. So basically, what we're going to do is we're kind of going to design like this portion of a mechanism like this. Okay. So what we're going to have is, if we look at this from the top, we're going to have two frame rails that come up the side. These are going to be constructed in kind of a weird way, out of sheet metal. We probably aren't going to work on these in the class. We'll probably, you guys probably have to refer to the video. Actually, we might hit these next week. It depends on where we get today. But it's gonna basically be two frame rails. There's gonna be bearings here. There's gonna be a shaft that goes all the way across. Okay. Basically, the drum roller. Do you guys remember the drum rollers? Do you guys remember how those work? So basically, it's a round aluminum tube, and then there's these two little like plugs, and they press into each end. You guys remember talking about that? That was a while ago. Remember talking about the drum rollers? Just gonna find a picture.
Talking about the aluminum tube that rotates.
Yes.
I don't know what you're talking
Can I type my own web address?
that
Apparently not.
Yeah,
Why did I name my company that? It's way too long. It's so long. All right, this guy here. So this is a little end cap, right? This is made out of aluminum. It's got a hex hole in the middle. And then basically, if I can go away. This transparent thing is just kind of a ghost, but basically you get an aluminum tube and then you press one of these end caps into either end.
They sell ghosts?
Yes, I sell ghosts. They're special ghosts. I only sell them in metric though.
Oh, only metric ghosts.
Only metric ghosts. Yeah.
Where
Okay.
do you get
What's the
them
name of
from?
your website?
Competition robot parts. We're gonna download CAD models here. Okay. So essentially, we're gonna have end caps, which look kind of like that. And then there's going to be an aluminum tube that goes over this whole thing. Now, we're not going to model it in our CAD model, but normally you'd put some sort of a rubber material on the outside of the aluminum. There's a lot of different options for what that might be, but you're going to put some sort of rubber. So we're going to leave some room. We're going to leave some room around the outside diameter of the roller, pretending that we're going to put some rubber there, but we're actually not because we're lazy. We don't want to model it. And actually, I drew this wrong. So the end cap's actually going to be about here. So on one side of this, we're going to leave a gap. In this gap, we're going to have a GT2 timing belt pulley. Okay? And then here, we're going to have a VersaPlanetary. We're going to have probably a bag motor, or maybe a 775 Pro, I don't know. But we're going to have a motor and a gearbox here. We're going to have a pulley here. We're going to run a belt between the two. And then we've got to have some sort of mounting structure to support the gearbox in that orientation. Now, this is a fairly typical arrangement because if with an intake, we can't put the gearbox here. Now, anybody want to tell me why we can't put the gearbox here? Anybody got any guesses?
Isn't there gonna be like something coming through there?
Well, I'm saying out here. Like, why can't we put the gearbox? Yeah, I mean the main reason is space. Another reason is also it's sticking out the front of your robot, and somebody could drive by and break the whole thing off. But basically, you want this to be as wide as possible. In FRC, we have space requirements. We're only allowed to fold out so far. And if I'm using 6 inches of that just for a motor, that's 6 inches of width that I can't have on my intake. So typically, you want to flip the gearbox around and put it kind of like inside the mechanism. Now sometimes you put the gearbox up top. Depending on what you're intaking, this gearbox might get in the way here. So you might want to put it on top, but for the purpose of what we're doing, we're not going to do that, just to keep it simple. So that's essentially the layout. We're going to do a layout sketch looking at this like in this kind of a direction, right? Looking at it from the side, just to lay out the center to center distance of the pulleys. The layout sketch is fairly simple. We're just going to, nothing in this CAD model is constrained, except I think this part is grounded, right? So you can't move this part, but you can just drag and pull this whole thing apart.
Can I please auto dimension?
No, not cool.
I wouldn't do that after just that.
Okay, so don't do what you're doing right now. Stop doing that. Use Control Z or use the undo arrow. So your whole gearbox looks like this.
Wait a second. Why
Yeah,
did
all the way.
Okay, so everything is in the correct position in the assembly, right? Everything imports and it's in the right spot. Okay, so when they exported the file, it was nicely constrained in SolidWorks, and they exported it. And then we imported it. Everything's in the same spot. It's just not constrained anymore.
What am I doing?
Because constraints work differently in SolidWorks for some matters. There's no way to import constraints universally. So,
Copy that.
well, yeah, so here's my next question. Are we going to go through and constrain every single part in this gearbox individually to the way it was?
Yeah.
Caleb and Micah are. The rest of us are not going to.
Hit the constraint button.
So what we're going to do is we're going to start down in the bottom corner. We're going to click and hold our left mouse button. We're going to drag a window around the whole thing. Then we're going to right click. We're going to go down to grounded, and we're going to check grounded twice. The first time you do it, it ungrounds everything. The second time you do it, it grounds everything.
I thought that was like a bad idea to ground everything though.
Yes.
Okay.
Oh, okay. Okay. Good to know.
So, you guys remember when I said it's a bad idea to ground more than one part in an assembly?
No.
This is basically the one case where you do it. When you're importing a complicated assembly from a step file. Now, if you really want to go through and constrain it, be my guest. But don't do it on my time. Don't do it during the build season. Do it whenever you want to on your own. Now, I've done some special things where I've kind of broken these up for my own use. I've broken these up into like multiple assemblies so that I can stick stages together
Highlight it and like
for stuff. So in those cases, I'll go in and I'll do some constraints, right? Just to
Just undid everything.
But here's the other thing. What are we gonna do? What are we gonna do to set the weight on this? Right? How are we gonna set the weight on this assembly?
Is there an option for weight in the assembly?
Yeah, so we're really gonna it's just gonna be the same thing we did with the motor. We're gonna override the assembly for the assembly, the weight for the assembly.
Yeah.
Now, that means something kind of specific for the stuff inside this gearbox.
There you go.
How important to us
Thank you, Matt.
is it that this is in here? Right? That our gear set is in there. Right?
That is so cool.
If we don't set the weight of the gears inside that gearbox and we set the weight for the whole assembly, we don't need all that stuff inside the gearbox. You could delete it if you wanted to, because all we care about is the outside of the gearbox. Now we're not gonna do that because that's just extra work to go in and delete the stuff we don't need. Might as well just leave it
We
there.
already grounded everything.
Right, it's in there, it's not hurting anything.
Okay, where can we get rid of you?
However, if you want to add stages or something, you don't need to worry about the stuff inside, just worry about the outside pieces.
I want to see the inside.
Okay, so now once you guys have grounded everything, you should be able to click and drag on any part and it should move.
Look at all.
Everybody got that? Hey, Andrew?
Which one?
Yeah. Okay, so does everybody have a 775 Pro motor? Does everybody have a thumb drive?
What? No, I don't have
Ben,
one.
when you're done. Okay, we're gonna download it again then. So we're gonna download this is the same motor we use for our spur gearbox model. So if you guys already have it, you don't need to do this. So If you have it,
I
just,
already have it.
okay. So for those of you who don't have the motor model from your spur gearbox, do what I'm gonna do. So go to Vex, go to the tab where it says motors and electronics, go down to 775 Pro.
Oh, I already did this.
Yeah, so if you have that CAD model on your thumb drive, you don't need to do this. So motors and electronics, go down to 775 Pro and
Yes.
click. Go to CAD files
I don't have a blue.
and download.
I don't have an upper left thumb. Do it.
Oh, you just left it. Oh, you just left
Shut
it.
down the whole tower.
Oh, last time I did like this, I just clicked on it.
Should I just move it to over here?
Copy it.
Bro, just shut the door down.
Yeah, cause I don't have it.
Really, you don't have to do that.
Okay.
You can just, you
But now I
can
can't
place
play
a
the
component. You try to use that key grab it. It's up to you. I'm going to put a second copy in there too. It will actually be, it's a bad idea to have two copies of the same CAD model in one project. So all of these, like my whole, my CAD class, in one project folder. You really don't want to have two identical
Well, now I
things
don't have anything.
under that full umbrella.
I'll just like
Shove this down.
So
Shove that down.
find that
Ooh,
copy.
yeah.
So if you really want one, you can go to that. Alright, everybody got that CAD model downloaded? Alright, so right click on it, show in folder, cut it out of that folder, go to your CAD class on your thumb drive, go to drum roller, and paste it in there.
What's on these? Your blaster. Oh.
It's
The entire. Every time you see it, yeah, but I watched this one actually. Satisfying Redstone contraption. Let's watch that. Wumbo Jumbo.
Why?
Logan
Why
Paul
not?
says
Oh my gosh.
fight Jake Paul on the one.
Why are you here?
Oh, Logan Paul and KSI.
Dude, who won?
That's not that happening. I want KSI.
Alright, so everybody got that model in their folder?
775.
Okay, so go into Inventor, go to Open, or I should say everybody who's doing this. Go to that folder, make sure all files is active, it should still be active. Click on the motor step file and open it. Click OK to the dialog when it comes up. And you should get this. Alright, everybody got that?
Are we removing the sketch and adding the work axis and all that again?
Yes, so delete the sketch out. So go over to the browser where it says sketch 1, right click on that, delete that. Now pick a work axis and just click on the body of the motor. That's fine. Alright, now you don't need to set the material. Generic is fine. But we need to override the weight. Only if you don't have the CAD model. If you already have the CAD model. If you did the gearbox
Oh,
project.
I have it on my thumb drive, but my thumb drive's at home. That's the problem. That's not good.
Alright, so now go right where over in the browser where it says the name of the part, all the way up at the top, right here. Right click on that, go to iProperties. Now go to physical, click update, right here on the top right hand corner. Where it says mass, select everything in that box and type in 0.8. and click update again. And it should default to pounds.
Okay,
That motor's 0.8 pounds, 8/10 of a pound.
Yeah, just
Look at that.
have the hand.
It's right there.
It's not on my waist, it doesn't count. Okay, so click OK. Give this a save. Then go back to your gearbox model. Everybody needs to do this. So all right, now everybody has a model of a motor, one way or another. Everybody has the gearbox pulled up. Now, our file name here says with bag. Because I'm lazy, I'm not going to rename it, I'm not going to bother. We're just going to delete the bag motor out of here, put the right motor in, and be done with it. So, select the bag motor. Delete the bag motor. You basically click on it and you click the delete key. That is how you delete things. If you can't figure that out,
Figured it out.
ask Andrew.
Andrew.
Oh yeah.
I figured it out.
Did you?
Select
Yeah.
that, and then
Congrats.
there's a point.
You can also find it in the browser right now.
It's like-
All right, everybody got the motor deleted out?
Yeah.
All right, so let's talk adapter plates for a second.
Dang it.
You see this plate here? This black thing at the back the motor was attached to? This is a special, it's a piece of plastic, and it's an adapter plate. It's got holes that the motor can bolt into. So basically you take that plate, you bolt it to the front of the motor, and then you bolt the plate to the gearbox. That's how you attach the motor. So you attach this plate to the motor, and you attach the whole thing to the gearbox. Now, there's a different one of these plates for every different motor. Okay? You can download the CAD. So we took out a bag motor. This is the plate for a bag motor. We're going to put in a 775 Pro motor. I'm not going to go and get a new model of the plate, right? I'm just going to slap the motor in here because the plates are all the same thickness, roughly. So I don't care enough, right? So you can see here for a complicated thing like this, I'm not being super accurate because I just want it to be roughly the same shape as the real thing. The only thing I'm really concerned about is this end, right? I want to make sure that all the mounting holes in the shaft are in the right spot, which I know they are. So I'm not going to delete this plate out. I am going to delete these two screws though. So select the end of the screw, select the other end of the screw and delete both of them. Leave the plate in there though. Now if you're really OCD or if you have some extra time, I think most of the gearbox assemblies that I've got on the Stellar like server, I think somebody has at one point or another put the correct plates in, so I think those models are right, but for the purpose of the CAD class we're not going to bother.
I can't crawl in it, like I can barely crawl in it, and I go over all this pipes from Wait.
Alright, so everybody
What
got
just happened? I just pressed the button.
Yes,
Well,
you did.
there goes your computer.
Bye.
All gone.
Oh, man.
Alright, so right click.
I'm just gonna,
Since I feel so bad, can I just turn yours off too?
no.
Okay.
Alright, so
What's happening?
now that you've got this, right click, click place
Computer's not
component.
even gonna turn on now.
Hey guys, pay attention. Alright, so right click, place component. So find your motor. Find your motor file, select your motor file, click open. Okay, now the motor is facing the wrong direction, probably. So right click, rotate by the y-axis once, rotate by the y-axis again. And then place the motor just somewhere over here. Just place it. Then press escape to get out of that tool. Alright, now we're missing something. This is a hex shaft. We kind of need a center line to constrain onto. Well, first of all, everybody get their motor placed in the right direction?
My computer, I don't know how to log in.
Caleb, do you know the login? Oh, okay, it's Stellar, lowercase.
Is it the username and password?
Username
Actually, just
Stellar.
have Andrew.
Yeah.
The inside of the hex shaft is round though, we can use that for an axis, right?
Well, the hazards obviously.
So guys, what we're gonna do is we're gonna add a work axis down the center of this gearbox, using what Caleb just said. The round inside surface of this, that's how we're gonna define the axis. So I'm gonna go click axis. Just FYI, we're in assembly right now. You can place work geometry in assemblies too. Right? You don't just have to do it in parts, you can do it in an assembly. So pick work axis, click on this inside surface of the output shaft. Now we've got an axis here that we can use.
Dang it.
It did not.
At least I have a stuff so I can just do it real quick.
If you, this axis isn't very big, so if you find it over here in the browser, and you right click on it, and you click auto resize, it does nothing.
It just
Alright.
All files.
Yeah, it didn't quite work there.
Oh wait, these are saved.
Alright, never mind.
I'm almost there.
Alright, so now we're gonna constrain.
So
So,
we're just going to ignore that the work axis doesn't go up for.
yeah.
Okay.
we'll just have to pick it up. Okay, so go to constrain.
Man, that's why
We're gonna
I use
constrain
the
this work axis here
I'm gonna use this.
to the work axis we just created.
Can we
I wanna-
use insert the insert
Dude,
tool?
it looks so
To insert the
beautiful.
shaft into the
Actually, we could.
back?
We could.
I'm gonna try that.
Actually, that's a better way to do it.
It's faster.
That's a good
Yeah,
idea.
my
That's all I
computer-
care
my
about.
computer
Like
just
literally in the
won't
video,
everything.
I did for the last project, that's like the first time I've ever used insert,
Really?
like for anything I was actually doing. Like I've done it before, I've just never actually used it.
What is this?
And I keep telling myself I need to start using it because it's, you know, better.
Well, I can tell you that too.
Right.
Use insert.
Alright, we're gonna use insert. Alright, so guys, go to constrain, go to this fourth button here that says insert, leave it on the default settings. You wanna pick this ring right here. Yeah, either this ring or this ring, but that ring's annoying, so pick this ring. Okay. Pick that ring,
I gotta ground it.
then rotate around to the back of the gearbox and pick this ring. Not this ring, this ring. Not this one, this one.
All of them.
Dude,
Not
the
with
hour.
oh my gosh.
Click on that.
What was the first
I'm gonna
one?
ground it.
What was the first one?
Which apply.
Why does that work?
What was the first one?
Grounded.
Nothing's supposed to work
That's true.
Jimmy, this one.
It's designed to not work.
Yes.
program.
Alright, so we have one
to
problem.
fail.
Anyone want to take a guess at what that is?
Cutting edge technology design.
There's
Name a width overall, we'll say, I haven't even thought about it, but we'll go outside to outside, 24 inches. Right, that's about the width of a robot. Okay, so we're gonna start with kind of the easiest thing here. We're gonna download a model of a VersaPlanetary and get it ready for use on our mechanism. So downloading models of VersaPlanetaries is a little weird for a couple reasons. So I want everybody to go to VexPro's website. Actually, just Vex Robotics. Then go to VexPro, which is the green icon. Then go to Motion. Then Gearboxes. And then it's down where it says VersaPlanetary Gearbox. Something I didn't mention earlier, there's also what they call a VersaPlanetary Lite, which is where it's just like a VersaPlanetary, uses the same gears and everything, except the outside casing of the gearbox is plastic, which saves weight. That's what you typically would use on an FTC robot, because you don't need the strength of the metal casing. In an application like this with a roller, you might be able to use a plastic housing, but I need to sleep. Anyways, Okay, scroll all the way down to the bottom of the Versa Planetary page. Where the tabs are, and click on CAD files.
Oh, there it is.
I knew that.
And Andrew, you want to make sure everybody's like getting where they need to go.
Why is yours green and mine red? What the heck? Don't like that. Everyone else is green.
You're on Vex EDR. You need to go back. You're at this one.
No, I'm not on that one. No, everything's green. It's just the text where it says please do download is red.
Yeah,
Oh,
he's the right thing.
okay.
Ha.
Okay, so click on CAD files. All right, so let's look at how the CAD files are given to us because it's not quite as simple. So, do you think that Vex has a CAD model for every combination of motor, gear ratio,
No.
number of stages, and output shaft?
No.
No, they do not.
They have layers.
So they give you each individual part that you can buy, and you can assemble the gearbox your darn self, which we're not going to do because forget that. They also, if you scroll down to the bottom of this list somewhere, no, not that one. It's not the bottom of the list. Where it says example V2 gearboxes, kind of in the middle. They've got single stage 10-to-1 with a bag motor, single stage 10-to-1 with an RS550, single stage 10-to-1 with a 775, single stage 10-to-1 with a 9015, versus Planetary 2-stage with a bag motor. So these are pre-assembled gearboxes. Now what we're going to do is we're going to download the one with the bag motor, and then I'm going to show you how to replace that with a different motor. Okay, because I think we're going to go ahead and model it with the 775 Pro just because I want to show you guys how to change the motor out. We could use a bag motor, but I want to just, if you're going to use a bag motor, you're just going to download the CAD model and it'll be done. So this is going to be a 2-stage arrangement. If we were, in our case, we're going to model it with 2 stages. If you wanted 1 stage, you could download one of these other examples. So go to where it says Versa Planetary V2 2-stage, 100-to-1 with bag, and download.
That does not sound fun.
In here, so it does the next
Saying it out loud.
So I'm making a folder called Drum Roller, which I'm going to keep all my files for this project in. All right, so
What are you naming it?
Drum Roller.
Okay.
All right, so once you get that file downloaded, right-click on it, click Show in Folder. If you're using Chrome, if you're using Edge, I pity you.
wild things.
I pity you.
The real thing is you didn't even mention Firebox.
If you use Firefox, it's kind of the same as Chrome.
Well, it's true,
Microsoft Edge is the future.
Microsoft Edge died before it was even released.
but true.
I like how when you search Google Chrome in Edge using Bing, it puts up like a half-page splash telling you all the reasons you shouldn't download Chrome. It's like Edge begging for its life as you're installing Chrome. It's great. It brings me joy when I'm working with a new computer. I'm like, yes, Edge, you know what you're doing. Oh,
Why isn't it working?
see, look.
And it searches it in Bing automatically. That's the future of searches, right?
You
Future
can
search
stream
engine.
videos 2.5 hours longer than Chrome.
Wait, what?
Yeah, how long
Whoa.
are those videos?
It makes your battery last 2.5 hours.
That doesn't even
Is
make
that because
sense.
it never loads the
It's
video?
over
Yeah.
Built-in assistance.
It's the keyboard. It takes 2.5 hours
Yeah.
longer to stream some. Okay. All right. Anyways, cut this file out of your downloads folder. Find a place for it on your thumb drive, and paste it in.
Somewhere in here.
Jokes on me.
Now, all right. I'm gonna give you a hint. I'm gonna give you a hint right now.
What's this?
When you import this is a step file, right? When we imported all of our other step files, they were single parts, right? They weren't assemblies. You can get step files that are assemblies. When you import them into Inventor, Inventor is going to automatically generate all of the part files and the assembly file. Okay, so this is a fairly complicated assembly that has a couple dozen parts in it. What's going to happen is Inventor's just going to kind of barf all of those files right into this folder right here. Right, so you're going to import this into Inventor, and all of a sudden this folder is going to be full of files. So what I'm going to do, just for the sake of cleanliness, I don't normally do this. Normally I just let it throw the files for it once, and then I move the files later. But I'm not going to make you guys do that. So I'm going to create another folder that's just called Versa Planetary, if I can type. And then I'm gonna just drag that step file in there, and that'll be how that is.
Folder.
Versa. Make sure there's an R in there.
Vesa Planetary. There we go. Also, why did you make a shortcut for this on edge? It's that folder.
No, it was in there. It was automatically in there.
Oh,
Because I don't have a thumb
Oh,
drive.
you're using-
Put it on
bring a
desktop.
thumb drive.
You're using Chrome. I'm going to put a shortcut to Microsoft Edge in every folder on your computer.
Yeah. Wouldn't that be
Microsoft just pre-installs that just so you just make sure you accidentally click on it.
Whenever you download Chrome, it just automatically overwrites it with garbage and replaces it with a shortcut to Edge. Yeah.
All right, everybody got that step file downloaded and placed in a folder. Andrew, we've got some people that are shaking their heads.
Where are they?
It's over here.
I had put it in the file.
Is anybody else having trouble?
You're welcome.
I am not.
I know Luke's having trouble, whether
I
he knows
am
he is or
not.
not.
I do not struggle, okay?
You don't struggle.
You go through hard times.
All right, so go to Inventor,
Yes.
go to Open. No, don't do me. You're gonna want to activate your project file if you haven't done it already.
Open.
I'm not telling you what to do. You should know how to do it by now.
Oh, wait, all.
I listen to all of
All
these.
files.
Thank you.
Not
What?
intelligence.
Are you sure?
Base of planetary.
That's what it is.
I should just CRP should just like launch a direct copy of it versus just call it a piece of planet and make it like pink or something instead of black.
Yes.
Just because.
I would get that.
And have it made in China.
I got it. I got it. Convert
China?
The worst plants
Oh
are
wait,
made
actually, I
in
should
China.
wait to do this in case.
So actually, I'll make it in the US and it'll cost 4 times
Yeah,
as
Is it gonna
much.
be a screen that
There
pops
we
up?
go.
Just because.
There's gonna be a little.
No, it's already there.
It'll be red, white, and blue.
I don't know what to do.
All right, everybody got that done? Everybody got Inventor up? Got your project activated? You click the open button.
You opened it like 3 seconds after me.
Go to the drum roller folder, go to your Versa Planetary folder, where it says files of type right here, this drop down list. Pick all files. All files. Pick the step file that you downloaded, click open.
You have to open it and then close the folder to make sure no one digs it.
You don't want anyone copying your work.
Yeah. You don't even want anyone to be able to see your work. Just
Yeah.
just
Just
encrypt
delete
it.
it. Just delete it already.
It's a good way.
Yeah.
Just delete
Well,
it.
You don't want anybody to see your CAD
Yeah.
copy, so you just don't see CAD. Gotta think about it.
Wow, that's genius.
Do I just okay?
That was
Do I
a
hit
wild
okay?
clock, I'm sorry.
Yeah, hit OK when that dialog
It
comes
was
up.
bad.
Even has the wires on it.
You see wires?
Cool.
Wait, I'm probably
You
looking-
see him. Wait, you see the
there.
object?
Yeah.
This worked.
I don't have any wires.
I gotta.
Just
you
keep
download?
looking.
Rotate. You gotta rotate around, Luke. Yours is
Oh,
gonna come up
yours
like
actually just doesn't
Mine
have
actually
wires.
just doesn't have wires.
I think you may have downloaded the wrong one.
I don't think I did.
Is it black and shiny with like little lip? Actually, that's a bad example. All the
Yeah, it
motorcycles
is.
are like that.
It's the exact same thing.
Is it round and looks like a motor?
Well,
you have V1 where they have V2.
Oh.
How did you download silly?
Wow.
They tricked you. You have to pay $5 to get the other one.
I don't know.
Don't ask me.
Yeah,
It's all Microsoft.
Do it. Do it again and do it right. We'll blame this one on Edge.
Yeah. Yeah.
Mean correction,
Of course,
everybody.
the Edge.
Do it again and do it right.
No, I don't want to say
Edge is
it.
the feature.
All right. Okay, so as of now, Inventor has not barfed a bunch of files into that folder yet. When you click the save button, Inventor will save all of those files, and then, so if I go to that folder right now, it's empty, there's nothing in here except this that folder. So if I click the save button, saves, takes a minute, takes several minutes, takes a couple of years. My grandkids are graduating high school. Actually, this is taking a really long time. Like I said, though, this is an actual CAD model of the gearbox. It's got all the gears inside and everything, so it's got a bunch of little parts with complicated geometry. So, now let's talk about weight for a second.
Next week.
How important
man.
is knowing how much a part weighs in CAD? How important is that?
Not very important.
Somebody kick Ben out. How important is it to know the weight of a component in CAD? Very important.
If you don't know, you might not have a robot.
Right.
You
So,
might not be
so
able to have a robot
if we
to
don't
help
have
you.
an accurate
No,
weight
no.
in CAD, what might happen?
Your robot might be overweight.
Your robot might be overweight. You might be like, oh, my robot only weighs like 3
Don't say
pounds in
over-
CAD. I'm gonna
don't
add
say
some more
over- don't
motors.
say overweight. See,
I'm gonna add giant bars of lead as structural elements.
There we go.
So you want to know how much your robot weighs in CAD, which means the only way to know how much your whole robot weighs in CAD is you need to know how much each individual component weighs in CAD.
Oh.
Right? Like buying blood. So basically what that means is that's easy.
down. You gotta go down.
Who's strong?
Oh.
No one.
Okay, so basically that's easy if you're modeling a piece of aluminum, right? If the part that you're looking at is a solid piece of material that's machined to shape, like a tube or a sheet metal part that's bent from a flat sheet of metal, you just say this part's aluminum, Inventor calculates the weight for you, you know how much that part weighs. That's easy, right? Motors are easy because it's one part and you know how much it weighs. So you guys remember when we went in, we overrode the weight of a motor? You guys remember that for our gearbox project?
Did the motor break? I don't know.
So we didn't care what material the motor was made out. We just said the motor weighs 0.8 pounds, right? And we just got that from Vex's website. Okay, and if that was one part, we were able to override the weight. So, are we going to go through this gearbox and set the correct material for every part in this gearbox to get an accurate weight?
Yes.
No. No, we are not. Now,
What? But what if you want to take it apart later and know how much each part weighs?
you don't. You don't want to do that. Now, if you're doing something weird, then yeah, I mean, if you want to do that, be my guest. If you want to go through and set the material, have at it. But I'm not going to. So,
You better get started now, dude.
Alright, so before you guys do it on your own, I'm going to show you something that's very, very, very saddening. This is a step file. As far as I know, Vex uses SolidWorks, because they're scum. No,
Or
they
maybe
use.
you're the scum.
There's a good chance of that. there's a very good chance. Anyways, so they're exporting this. They're exporting this from their CAD system, and then we're importing it using a step file. So does this assembly have all the nice constraints and everything like an inventor model would?
I don't know.
No, it does not.
Yeah, you can do that to the actual motor, right? Just pull it.
So now,
It,
what's the problem with the assembly that we've created so far? What are we missing?
it doesn't have screws.
We're not gonna actually put the screws in,
Oh,
but,
okay.
but you're kind of on the right track.
It's not actually connected? Question mark?
Oh,
Spinning around.
I'm supposed to
Do we care though?
Well, actually, that's a valid question. No, not really. But we're gonna constrain it to stop that anyways.
Aw.
Now, if we were using the right plate, which we're not, but if we were, we could constrain to the screw holes in the plate, and that would solve the problem. However, we're not using the right plate, so we can't. So what we're just gonna do is I'm just gonna go to constrain. I'm gonna go to the angle tool, which is the second one in this list. So click on that. Then I'm gonna click on this directed angle one over here on the left, right here where my mouse is. I'm gonna click on that. Then I'm gonna click on one of these little tabs. Click on the tab.
No.
Click on the top of the gearbox.
Come on. Yes, it cannot be placed in itself.
What is happening?
I don't know.
Okay.
And then click OK.
I'm just clicking all
That'll
the
just
wrong
stop the
buttons.
that'll just stop the motor from turning.
Wait, what?
I'm clicking all the wrong buttons. Open.
Have we
Yes.
Have you ever explained what each of those options for angle do? Because if you did, I don't remember you doing that.
I'm not.
Rotate.
I never used the middle one.
Rotate.
I used the first one.
Add your mouth.
No.
As far as I know,
That.
Oh wait. Okay.
No!
the only thing I know is that the end one, the one on the right, directed angle,
We're breaking.
no, explicit reference vector. Basically, you have to define the center line axis that's used to measure the angle.
Alright, you can do it.
Right, so you basically have to say, here's one direction, here's the other direction, and here's the normal of the axis used to measure that dimension. It's kind of done with.
Okay.
But basically, the option that we just used, my understanding is that positive angle and negative angle is kind of not well defined.
Okay.
Right, it can be either, and that might actually be the case. I don't know for sure. It might, the constraint solver might be able to flip it one of two directions.
Okay.
If you use the explicit reference vector, that's not the case. Basically, you have to use explicit reference vector if you want to use an angle with a range. Right, so I got like an
So
intake.
basically, we just put a flush constraint on the surface of that tab.
Well, it's not a flush constraint because they're not flush, but yeah, it's kind of the same thing. And that's when I use the left one. If I'm actually controlling an angle I care about, I use the rightmost one.
Okay.
We're not really going to go over that in this class just because it's obnoxious to work with, and I'm going to try to explain it. And you don't use it that often. I mean, you'll use it to constrain mechanisms on your robot assembly, that's about it. Okay, everybody got this? Everybody should save. Now we have one more thing we need to do. What is
All by
the,
myself.
what is the one thing we need to do?
Put it on.
I heard somebody say wait. Whoever said wait was right. I don't know who said that, but whoever said wait was right. Okay. So right now, remember, we can override, like we just did for the motor, we overrode the weight. We just told it, this motor weighs 0.8 pounds. I don't care what you say, inventor, the motor weighs 0.8 pounds. So what we're going to do is we're going to do that for the assembly. We're going to say, this gearbox weighs this many pounds. I don't care what you say, this gearbox weighs this many pounds. So, right in the browser, right-click on VersaPlanetary, go to iProperties, go to Physical, click Update. Now, how much does the motor weigh?
point
Wait,
eight.
I don't let you do that.
I heard a whole lot of wrong answers. I did hear some right answers.
1 pound.
No.
0.997.
No, the motor that we just did.
Isn't it
Point
It's
eight.
0.8 pounds. Okay, so if we go to Vex's website, you guys don't need to do this, but I already pulled it up. If we go to Vex's website, on the VersaPlanetary page, and we go down to where it says weight, they tell us how much the stuff weighs. So we can see that a 2-stage gearbox weighs 0.744 pounds. So are we gonna type 0.74 into this box?
No,
Very good. So what are we gonna type into that box?
that plus a 77 pound motor,
Yes.
question mark?
Yes. So if the gearbox weighs 0.74 pounds and the motor weighs 0.8 pounds, how much does this thing need to weigh?
0.74
More than a pound.
Yeah, but what is
Yeah.
that?
I don't know.
You could probably just type the
You can't just
equation
type it in
into the
there.
box if you
Actually, that's a
wanted
good
to.
question.
It works for me.
This box.
Did it work?
All the boxes.
How angry
So-
would Inventor be if you made it less than 0.8, but made the motor
Not
more?
not mad at all.
Oh, okay. It just doesn't.
Actually,
care.
we didn't need to set the weight of the motor. The only reason I had to do that is just because you might use that motor in an assembly that wasn't in a VersaPlanetary.
Relative error.
So it's good practice to always set the weight
I just didn't.
of a component that you might use by
It
itself.
doesn't care if two weights directly contradict.
Yeah. Because that's the whole point. This is an override.
Yeah.
Right. Okay, so type in 0.8 plus 0.74 and click update again. Should be 1.54 pounds. I've never typed
Math
that.
is the same
It's
everywhere.
actually
I guess I should practice
1.540.
when I reach. If there's a box, you can type an equation into it. Alright, so click OK. Alright, now, that's all we're going to do for now on the gearbox. We're going to just close it. We'll come back to it later in the project.
Wait, I better save this so I don't turn off my computer.
Actually, I should have
Yes,
closed
you
that.
have.
Crap, dang it.
Oh,
Wait,
Inventor's
0.8
not
times
responding.
See?
That's fun.
20 times what?
0.8 plus 0.74.
Don't try and save it. Just don't try and save
The
it.
gearbox weighs 1,327
Don't
pounds.
save it. My computer is about to die because I tried to save it.
Before we die, we better put it as
Let it save. Did you not save it earlier?
We better put it as
I saved it earlier.
Me too.
Autodesk Inventor Professional 2018 is not responding.
Oh, you gotta redo everything. Get
Yeah.
wrecked. Actually, if you didn't save your gearbox, you're gonna have to start over.
That's what I did.
Whoops. Now, you guys remember when I dove under the table and turned off the computer by hitting my button?
Yes.
Yeah, that's what kind of what I just
Don't touch
Is that when Kai walked
Don't
in?
touch
did.
anything.
But while it's not responding, we better put
The
it
other was when Kai walked in.
I'm just gonna like.
Alright, anyways.
I'm just like.
Alright, so we've got 6 minutes.
Control.
Plenty of time.
Yeah, no, but, alright,
Yeah.
this was really the important thing I wanted to show you anyways. We're not gonna do the layout sketch. We'll do the layout sketch next week. I'm gonna show you what the layout sketch is though by drawing it on the board. I'm not gonna try to do it in CAD. Alright, so we're gonna, remember we talked about this layout. Does this make sense to everybody?
Yeah.
Okay, so we're gonna look at this from the side. So I'm gonna draw it here. So this is my drum roller. Okay, that's 1.25 inches in diameter. Okay, right. Alright, so the gearbox is roughly a square. Okay? It's got some weird lumps on it, obviously, because of the little mounting pads, but it's roughly speaking a square. So there's some little bits that stick out on either side like this. However, we're not going to draw those in our layout sketch because they're not important. Now, if we were putting this close to something and we wanted to make sure they weren't going to hit, we might draw those in just to make sure that they cleared, but we're not going to be anywhere close. So now, so we're going to draw a square in our whatchamacallit? Layout sketch. Thank you. And that's going to represent the gearbox. So basically, the whole design thing that we're trying to do here with our layout sketch is we're going to figure out the center distance from this shaft to the gearbox shaft. Alright, so let's talk about some of our design constraints here. And then what I would like to see if you guys can do is if you guys can make this layout sketch, figure out what this center distance is on your own before next week. I'm not going to give you very much information, but it's not hard. So we need to pick out a pulley. Now, we're going to do all of our gearing in the gearbox. Okay? We're not going to do, now we could put a small pulley here and a big pulley here and do gear reduction through our belts. Right? And on an actual robot, we might do that. However, for the purpose of simplicity, we're just going to have a one-to-one belt stage, right? We're just moving power. That's all we're doing with the belt. We're just moving power. So we need to pick a pulley. We need to pick a marker. We need to pick a pulley that will fit on the gearbox, and we need to pick a pulley that will fit on the drum roller shaft. Now, if we're going to be pulling a game piece in here, we really don't want the pulley to be bigger than the drum roller, because the pulley will get in the way for obvious reasons. Now, I said earlier that we're going to have some rubber on this roller. So it's going to be bigger than the actual diameter of the roller. I just added 3/8 around it in the layout sketch I did for the handouts, which is a pretty safe number. And so basically, our pulley can be bigger than the aluminum. We just don't want it to be bigger than the rubber. So what I did was I went to VexPro's website. I went to Motion. I went to belts and pulleys. I go into quite a bit of detail in your CAD handout about what I picked. And I'll talk through this again in the video. We might talk about it again next week. But I went down to GT2 timing pulleys. If you guys remember, when we were talking about timing belts, GT2, we use HTD for kind of big stuff, like our drivetrain. We use GT2 for small stuff like rollers. So we use a GT2 timing pulley. There's only a few choices. We're going to go with this 36 tooth one, which ends up being, maybe yay big. It's fairly large. Maybe a little larger than I'm comfortable with, but the 24 tooth one's really small, and we only have two choices, really. And then obviously the 48 and the 60 are really big, so we don't want to go with those. So both of these are actually going to be the same size. Then we're going to have a belt that runs between them. So basically, really quick, got a couple minutes here. If you go to Motion, well actually no, I just clicked back. Okay, so where it says here GT2 timing belts, there's a list of belts, 45 teeth, 50 teeth, 55 teeth, all the way up to 180 teeth.
That is a lot of teeth.
Those are our choices. We have these choices. So we know that our timing pulleys have 36 teeth. We want to know how long our belt needs to be, which one of these belts we're going to use, and what the center distance is going to be between the two. Okay? So there's this nifty calculator. I want you guys to get used to using this, so go ahead and follow along on your screen. You go to Chrome, go to sdp-si.com. sdp.si.com. Now, if you remember, I showed you guys this website before. You can buy timing belts and stuff from these guys, as well as other things. If you go up to where it says Design Tools up at the top, and go to Center Distance Designer, you click on that, it should take you to this page. Everybody got that? Andrew, you want to help him out?
Wait.
Oh wait, a second. This one. Got it.
Yeah, so you're going to go to sdp-si.com,
And then down.
Design Tools, Center Distance Designer. Second one from the top. Click on that, you should get here. Okay, so under unit, we're going to be in metric, because GT2 pulleys are in metric. Our pitch is going to be not 2mm GT2, it's going to be 3mm GT2. Okay, so pick 3mm GT2.
Then leave metal timing pulleys alone. Pick from the drop-down list, go down to 36 teeth for the tooth count. On the other pulley, pick 36 teeth because they're both going to be the same. So where it says pulley A, 36 teeth, pulley B, 36 teeth. All right, now there's two ways you can use this. You can type in where it says desired, you can type in a center distance. You can type a center distance that you would like in millimeters. So if we wanted it like 2 inches apart, you type in 50 millimeters. It'll give us the next belt up. It'll give us the next center distance larger than the number you put in. Okay? With a belt of a reasonable number of teeth. Okay? Now, you can type in 100, right? It'll tell us we can get with a 100. Now down here it shows you how many teeth the belt has. 103 teeth. With a 103 tooth belt, we can get 100.5 millimeter center to distance, which is pretty close. Now, that's great if you're buying from SDP. However, we have to buy from Vex. So you can go to Vex and you can look and say, you know, here's a 100 tooth belt. Right, what's my center distance with a 100 tooth belt? So click the drop down list under belt and pick 100 teeth. And then this right here, this number right here on my screen tells you what the actual center to center distance is, 96 millimeters or 3.7795 inches. So basically what you're going to do is you're going to draw a layout sketch. You're going to figure out the diameters of your pulleys. You're going to draw in your roller. You're going to draw in your circle for your rubber. You're going to put the gearbox in there. And basically you want to get these two things as close together as you can, right, to save space, right? You don't need this way over here. That's just a waste of space, unless there's some reason you need to put it farther away. I mean, in that case you would, but in this example, no. You want to put it as close as you can while still having a nice gap between the drum roller, the rubber, and the gearbox itself, because you don't want them to be hitting. So you would just go down the list of Vex's belts, pick one that was close, and use that. We'll go over that in more detail next week and in the videos.
So did you say we're doing this over the week?
I would like you to try. We're going to cover it next week, but I would like you to try.
To have it done?
Just mess with it. I want you to
Just calculate?
yeah, the calculator and making a layout sketch. So the roller is 1.25 inches in diameter. You guys have a CAD model for the gearbox. You guys can figure out how big the gearbox is using the measure tool. 36, and then there's I think, yeah, all this information is in your handout. Which pulleys we use, and I actually go through the process and I pick a belt. So review it, look at your handout. That'll tell you everything you need to know. All right, good job, guys. That's going to be it for this week.